but because I believe AP Central does. When we talk about potential energy, there is a very distinct difference between kinetic energy and potential energy. Kinetic energy is all about an object. It is something an object has, and all an object has to be doing is moving for it to have kinetic energy. Yesterday, when we developed the work done on a spring, we said that this was potential energy. In fact, what I actually think we did was something like this. I think we said that the work done by you on the spring was 1/2 kx squared, but the work done by the spring was negative 1/2 kx squared. Is that where we ended up at the end of the class yesterday? Is that about right? The negative sign is important because you pushed on the block went in the direction you pushed it. That's why the work you did was positive. You are an external agent, and you are acting on the block. You are an external force. The spring is being compressed. It's trying to push itself back into its original position, but the block is moving in the opposite direction, so the work done by the spring is negative. You guys follow all that? The block, which was pushed up against the spring, and it started somewhere over here, and after a force was applied to it, ended up over here, compressing the spring. Something like that. And we pushed the blocks this way, with our applied force this way. This was you. The spring the whole time was pushing back. Okay? All familiar to yesterday? Once we've done this, we could just kind of put a little pin here and hold that block right there. That energy is stored in this system. Here's the first thing to understand about potential energy. There's no potential energy in the box. The potential energy is in this system. Potential energy is always stored in a system of elements. A single object does not have potential energy. A system of objects or elements has potential energy. Although for us, we're only going to see 3 or 4 different forms of physical potential energy, all forms of potential energy is the interaction between an object and a force and another object. In this case, it's the box, the spring, and the retainer holding the spring. Without this retainer, the spring can't be compressed. It's this interaction between the box and the spring that's what stores the energy. The box can't store the energy alone, and the spring can't store it without having a stopping point, a point of reference upon which it's being compressed. So all forms of potential energy are an interaction between 2 or more objects. All forms of potential energy. Next, we will define potential energy based on the conservative force doing the work. This is important, and it sounds subtle, but you're going to need to use this. We're going to define potential energy by the conservative force that does the work. So you applied an external force to the system. The spring was the conservative force. So we define the change in potential energy is minus the work done by the conservative force. And you might be saying, well, why don't we just define it based on you? That one's already positive. Why are we putting this negative sign here? There is a very important reason why we do this. And it won't be clear for a few moments. So just bear with me. But based on that analysis, right now, we would say that the elastic potential energy, the change in elastic potential energy, is equal to 1/2 K delta X squared. We're going to put an E here to indicate that it's elastic potential energy. Every form of potential energy will use a capital U and a subscript to define what type of potential energy we are discussing. Everybody good so far? Now, this took longer in the other classes to develop than I anticipated. I don't want this to take very long here. I want you to consider what it would take to lift a box and put it on top of a shelf. It's not going to be a surprise that there is gravitational potential energy. So this is you. You're going to lift the box. When we talk about doing work here, there's going to be two forces acting on the box. Both of them do work on the box. So I want you to consider the least amount of force necessary to move the box from the ground to the top of the shelf. Let's say the shelf is H high and the box has mass M. Is it a huge surprise to think that in order to lift the box, you would have to apply some upward force? This is the force supplied by you. How much force do you have to supply to lift the box with the least amount of force to get it to the top of the shelf? I've asked this in every class, and every class has given me this kind of pause. At least the weight. That's all I wanted to hear. That's right. There are two forces acting on the box, you pulling up and weight pulling down. If I want the least amount of force necessary to lift the box, I have to lift the weight of the box. Not a hard question, right? We all good so far? So if I am going to place the box successfully on the top of the shelf, like so, there's the work done by you. That'd be your applied force times the height you lift the box times cosine 0 degrees, right? You lift upwards on the box goes upwards. Does that make sense? There's the work done by gravity. Can we all agree that that would have to be mg? Right, the force of gravity times h times the cosine of 180 degrees, because gravity is acting downwards, but the box is moving upwards. And is it too big a stretch to say that the least amount of force would be when you push up with mg? Is that good so far? If I push up any harder, then I'm also going to change the box's kinetic energy, and I'm not really interested in that. I want the least amount of work done in lifting the box. Now, this all to say that the work I do is mgh, and the work gravity does is negative mgh. You all see that? Net work is still 0. In our prior discussion, we'd say that there's nothing different about the box, and there isn't. The box doesn't have a change in energy. But we separated the box from the floor. There is energy stored in the box-earth system. There's a gravitational force still acting on the box. Should the box be pushed a little bit off the shelf, that force will bring the box right back down, correct? So we state that although the box doesn't have any more energy than it did, the net work done on the box was 0, the box-earth system increased its amount of energy because we separated the box from the ground. I know this sounds like a weird distinction, but this is the way I'm supposed to be formulating it now. The box didn't change, the box-earth system did. And how much did it change? Well, the change in the potential energy of the box has to be minus the work done by the conservative force. That means the change in potential energy of the box has to be equal to mgh for the box. But Mr. Shelton, isn't that what you did? No. We say this energy is caused because of the conservative force, not because of me. I did change the location of the box. It was me that gave the energy to the system so that the box could now be on the top of the shelf. But that energy resides with the system. The system has this energy. And just like there was no energy in the spring unless the spring was involved, there's no energy here in the box unless the earth is involved. Is that good so far? Following along okay? Now, I want to make a 2-minute analogy and discussion real quick. This suggests that anytime you lift an object above the ground, it has energy, that it and the earth somehow now have energy together. The problem with that statement is that it makes some weird assumptions. For example, the battery on my desk. I know it has electrical potential energy, but does it have gravitational potential energy? It's a weird question to ask, because I think most people know I'm trying to bait them into a trap. Like, why wouldn't I say that? Didn't we just say that if it's above the ground, it has gravitational potential energy? You got to think about the word potential means here. Is it very likely that when I come to work tomorrow, the battery's still going to be sitting on my desk? Is there much of a chance it's going to fall to the floor? The thing about potential energy is about the potential to do work. I pull the arrow back against the bowstring in the hopes that I could release the arrow at the time of my choosing. Similarly, I didn't put the battery there for it to have gravitational potential energy. But the battery there, well, to hold my stocking and to do a lab that I was doing in the other class. For the same reason that most of you don't think the water bottle is going to fall off your desk. You didn't put it there with the purpose that it would fall to the ground. Now, if I wanted to use this energy, well then, in the course of lifting the object, how much I lift it might be important. But when I ask you if the battery has potential energy, what you really should ask me is relative to what? Where's the ground? You understand why I'm asking that question? Because it was brought from the first floor to this floor originally, and then lifted from the floor of my classroom to the top of this desk. Potential energy has to be used in a functional way. So if the battery never falls to the ground and is sitting in the middle of my desk for eternity, does it have potential energy? Well, work was done to get it there, but the idea of potential energy is to have a use for it. Let me kind of go back to this example we had over here. I might have put the box up there on purpose because maybe there's a nail on the floor over here, and I would like to drive the nail by having the box fall on the nail. Like lifting up a hammer to bring it down on a nail is the same kind of process. I want to use the energy I put into the hammer by lifting it, by letting gravity do the work in driving the nail. I can push on the nail, but that'll probably hurt. And I'll probably be able to get more energy delivered to the nail by dropping a box on it or dropping something heavy on it. The moment the box clears the edge of the cabinet, gravity will do work on the box. It's the only force acting on the box, correct? So if we look at that scenario, if we look at that scenario of the box falling, the only work that's going to be done is the work done by gravity, which is going to constitute a net work scenario, right? That means that's going to equal the change in kinetic energy. Everybody following along so far? This is the crux. This is what I need you to know. Change in potential energy is defined as minus the work done by a conservative force. But if the only force doing work is the conservative force, then the change in potential energy has to equal minus the change in kinetic energy. A transitive property, correct? If there's only one unbalanced force doing work, that work changes the kinetic energy. And you're not surprised. If I drop the box, would you all agree the kinetic energy of the box is going to change? That makes sense, right? Here's the important detail right here in this little piece. Delta U is U final minus U initial. Delta K is K final minus K initial. I don't know if you're going to see what I'm going to do here, but if I distribute the negative sign, I can collect the initial conditions on one side and the final conditions on the other. So I could have UF plus KF on one side and UI plus KI on the other. And if you don't see what this says, let me spell it out for you. If only conservative forces act in your system, then the total amount of energy a system has before you're observing it has to equal the total amount of energy the system has later, meaning the total energy of the system stays the same. It can go from one form to another, but the total amount of energy stays the same. So in this example, that while the box is falling, it has potential energy when it's here. As it falls, when it reaches some point in the middle, it's got a mixture of both, right? It's still above the ground, so it still has potential energy, but it's moving now, so it has kinetic energy. The total has to stay the same until some external force, the nail, applies a force to the box to take that energy away. This concept is called conservation of energy, and it's a very powerful concept. There's two reasons why it's so powerful. First, conservative forces are path independent. Meaning you don't have to take a straight line to go from one place to another. They are path independent. I could have a slide that looks like this and put a box on the top. It would still have to follow these rules, even though I never know what the angle of the slide is. And we'll get the second important detail tomorrow.